Welcome to CSC7132, Operating Systems and the Networking. This is Brady. In Module 2, we're going to cover the processes, threads, and the resources. So we're going to divide the Module 2 into 3 video files. Now the first one going to cover the Section 1 and the Section 2. Okay. Now Section 2.1, the process concept. Now in this section, we're first going to introduce the concept of a process. Now what is a process? Now a process is an instance of a program being executed by OS. Now here we have two concepts. One is a program. Now the other concept is a process. Now what's the difference between these two? Now we know a program is a software. A program is a code. Now what is a process? The process is not the same as program. Now let me explain this. So let's say we have a computer system. A computer system has a couple of components, CPU, memory, and let's say hard disk. Okay. Now these components are connected through the system bus. Now the hardware is actually connected to the system bus through a disk controller. So sometimes it's called a disk controller. Okay. Now a computer may have some other peripherals. For example, definitely most computers are going to have a monitor, and it is connected to the bus through a controller as well, but sometimes it's called a graphics card. We may have a keyboard, mouse. Now keyboard, mouse many times shares the controller. This is a USB controller. Okay. So when you install a computer program or computer apps on a computer system, you basically copy the programs to the hard disk. Okay. Now let me actually use different color to illustrate the concept. So you basically, install your program on a computer program. So I install, let's say, program 1. And then I install another program, program 2. Okay. Now, program is a static thing. Program basically stays on the computer hard disk. It's not going to run by itself unless you triggers it. Now, what's the process? Okay. So let's say when you try to run a program, let's say I want to run a program 1. So then typically you're going to trigger the program by clicking the icons of the program on the computer Windows, desktop or Windows, or you can type the command by, on the actually Windows command line interface. Okay, so anyway, you're going to trigger this program. So this can actually copy your code into the memory, somewhere in the memory. Okay. Now, once the programs is copied into the compute memory, then this program start to actually, fight with the other program for the CPU. So once CPU is free and CPU can actually pick the instructions in this program 1, pick up the instructions and start to execute. So you're going to go through a cycle called fetch, FETCH, and then the CPU going to decode the program, the code instruction, and then execute the instruction. Okay, so now CPU going to do this through a high-speed connection. Okay, CPU does not go through the bus. So let's say here's the high-speed connection. So CPU going to actually fetch the instruction. Okay, and then decode and execute. So it's a cycle. So when CPU's, once you actually click the program 1 and load the program into the memory, and then the program start to actually fight with the other program for CPU resources. Now, once you start this program and load it into the memory, and then you basically start a process. So process is dynamic thing. And sometimes they call process a thread of control. Okay. Now, once the programs loaded in the memory start to actually to run, then you're going to run following the order of the instructions. Now, that's called a thread of control. So that's the process. So that's the reason why in many books, people call process a program in execution. Sometimes I like this definition. It's very short, but it's very clear. So it means that it's not a program, but it's a program in execution. Okay. So modern computer systems basically support multiple processes. Remember, we call this multi-processing, right? So that means a computer system can load multiple programs into the memory. So that means, while program is 1 is loaded into the memory, I can load the program 2 into the memory. Okay. So now I have 2 processes running. Now I can load another program into the memory, so I have 3 processes running. So now a computer system may have multiple processes. So now the operating system keeps track of each process using a data structure called a process control block. Okay, process control block is a data structure that record the status of each process. So that means for each process, the operating system is going to create a process control block, and sometimes we call it PCB. So if the computer contains 100 processes running concurrently, then there are 100 process control block, 100 PCBs, created. So this is the data structure that holds the information for a process. Okay. So what kind of information is stored in the PCB? The PCB actually stores the current instruction address. Okay. Because when CPU try to run a program, CPU gonna fetch the instruction. And once you fetch the first instruction, execute the current instruction, and then the next memory address, the memory address of next instruction going to be stored in the CPU as well, so the CPU know which is the next instruction I need to run. So So that's the information that will be stored in the PCB. It's called current instruction address. And then the execution stacks during the execution, then you're going to actually create some temporary memory space to store the temporary data. The set of resources used by the processes and the program being executed. And so the PCB is the concrete representation of a process. So every time when a process is created, you create a PCB. Okay, as was mentioned in the previous slide, a process is a program in execution. Now, a modern computer may support multi-processes. So that means multiple processes are running concurrently. So that means these processes are basically fighting for the CPU resources. So if the CPU is available for the process, so then CPU start to execute the instruction for the process, then this process is running. Now, what about the other processes? Now, the other processes are basically in the idle state. That means they're ready to run, but they currently don't have the resources, the CPU resource. So because of this, a process may have a couple of different states. Okay, so the number and the type of states varies between different operating systems. But for most of the operating system, they implement at least 3 basic states. So one is the running state. And there's another state called the ready state and the blocked state. Okay. So remember, once the process is created, so that means once we click the icons for program and load the program into the memory, and then a process is created. So this process is going to be loaded into program is loaded into the memory. So that process is normally in the ready state. Okay. It may not actually, the CPU may not be available. So that means it's ready to run, but it's currently not running. Okay. And then once the CPU is ready for this process, and then CPU start fetch the instruction for the program and load the instruction into the CPU, then this process is now in the running state. So the CPU keep actually, fetching the instructions, from this program, and then suddenly one of the instructions going to ask the programs to, use the I/O or for other, hardware devices. Then this process may block itself because it's not going to use the CPU. It may use the some of the peripherals. So that's called a blocked state. Okay. Now, once the process complete the I/O operation, then the process is going to be, say, I'm ready. So in that case, most operating systems are going to put the process in the ready state, and then fighting for the CPU again with the other processor. So these 3 states are basic states in pretty much in all the operating systems. They implement these 3 states. Now, some of the operating system may implement some more states. Okay. So typically, the process, once it's created, it's going to be in one of these states. So a transition from one state to another is performed by the operating system. Okay. But it may caused by process itself. For example, like I said, when the process is running, suddenly process is requesting for the I/O, and then the process is going to be blocked. It basically a block itself. Okay. Or sometimes the class is going to be blocked by another process, or so there's various different ways that the process is going to transfer from one state to the other. As was mentioned in the previous slide, so in most operating systems, a process has at least 3 states: ready state, running state, and blocked state. Now, however, most of the operating systems provide a more complex set of states and transitions. So here are some of the examples. Now, in some of the operating system, there's a newly created process may placed into a new state. So a new state is not a ready state. So that means the process is created. They put in the queue, but they are not ready to fight with the other state for the CPU. So that's a new state. Now, in other operating system, a process may have another state called a terminated state. Okay, so once the process completes its job, then it just terminated by itself. Okay, and the process may place into a suspended state. Okay, even though the CPU and all resources are available, so for whatever reason, a process operating system may want to stop a process to allow, for example, debugging or to regulate a performance. So there's possible that in most operating system, a process may have more than 3 states. They may have 5, 6, or even 7 different states. Now, another important concept in the operating system processes is called the context switching. In a multi-programming environment, multiple processes are running on one computer system. Okay, sometimes there's only one, many times there's only one CPU. So now there's one CPU and the multiple processes running on this CPU. So remember, so if you have multiple processes, each process is associated with a program, right? And now, suppose I have 4 processes running simultaneously. But you know that at any particular time, the CPU is only running one process. So that means the CPU is only executing the instruction of one process. Now, CPU, they may switch to another process and stop the current process and then switch to another process. Now, after for a while, CPU may switch to another process. So each time one process stops executing to allow another one to resume. So that's the kind of scenario that the CPU actually move back and forth among these different processes. Now, so a context switch is the transfer of control from one process to another. So if you look at the timeline, okay, here's the time. Now here's the process 1. Let's say process 1, process 2, 3, and 4. 1, 2, 3, and 4. Now let's say we start from time 0, and the CPU is running process 1. And after for a while, CPU going to switch to another process, process 2, and process 3, and process 4, and then back to process 1. You're going to continue that way. Now, a context switching is basically the transfer of control from one process to another one. Okay. During this time, the CPU need to remember. Let me see. Once a process is created, there's a data structure called, if you remember, it's called a process control block, right? PCB, 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 PCB. Okay. Now, when a CPU switch from one process to another one, from say process 1 to process 2, now that's called a context switching. Now, each time, during the context switching, the operating system must save all the information about stop the process. That means every information about the process 1 will be saved. Where is this information going to be saved? Yes, it's correct. It's going to be saved in the process corresponding to process 1, at the process control block corresponding to process 1. So it's going to be saved in PCB 1. Okay. Now, so once the process 2 is done, the CPU wants to switch from process 2 to process 3. That's another context switching. And then the information about process 2 will be saved in PCB 2. And then the CPU going to load the information about the process 3. Now, where this information for process 3 going to be loaded? It's loaded from process PCB 3. The information will be loaded from PCB 3. And then the previous information will be saved in PCB 2. So remember, so that information will be saved in PCB 2, and the PCB 3 information about PCB 3 will be loaded. Now, once the CPU actually switches from other process to process 2, now that saved information will be loaded back to the CPU. Okay, so that's the context switching. So that means now many times when we say, okay, I switch from process 1 to process 2, and from process 2 to process 3, it sounds very easy, but during this time, the context switching happens. And the context switching takes some time, because when you have to save the stop the process into the information, the state of the stop the process into the process control block, and load the next process, load the information of the PCB of the next process into the CPU. So you have to do this. So the context switching takes time. But most of the time, we choose to ignore the context switch time, because compared with the running time for the process, the context switch time is relatively small. But if you actually can't do the context switching very frequently, maybe you have to think about the time. It's an overhead. Okay. Now, so the information that need to be saved into the PCB is called a CPU state. So when the process is running, the instruction of one of the instruction of the process is going to be in the CPU, the state of the instruction. Now, also some of the data loaded into the register of the CPU. All this information should be saved in the PCB. And then next time when the CPU is back to the process, all the saved data can be reloaded into the CPU and then continue the execution. Okay, so that's the context switching. Okay, now let's switch to the section 2.2. Why we need to introduce the processes. Now, one of the big advantage for the process is that it just gives us some kind of flexibility. Now, modern computer systems are very complicated. Some of the system may have only one CPU. Okay. Now, some other systems may have multiple CPU, and sometimes we call it multi-core system. So, for example, if you buy a PC, the chances are that you your PC may have like 8 cores or 16 cores. Now, each core is an independent CPU. It's a dedicated CPU with its own, own clock. So in that case, if you have a multiple processes running on the system, and you have a multiple CPU, then you can actually, the operating system can optimize the usage of the system. They can manage the processes to different CPUs. So make sure each CPU has something to do. Now let's take a look at a simple example. If we have 8 processes, okay, and you have 8 CPU, so then you can allocate one process to a CPU, a dedicated CPU. So now each process is running on its own CPU. This is good, right? Now, what about if you have 8 processes, but running on a single CPU system? So there's only one CPU. Okay, so now in each case, it's like you have 8 processes, and then running on 8 CPU system, 8 core system. So then you can allocate one process to one CPU. Okay, this is going to actually make the system more efficient. Now, what about the 8 processes and only one CPU? Then remember, we have a technique called time sharing, right? Time sharing is a technique used in multiprocessing. It is a multiprocessing. So that means CPU gonna actually execute one process at a time, and then after a certain period of time, CPU gonna switch to next process, and then switch to next process. Remember, if the CPU is very fast, for example, CPU is running very fast, like a 4 gigahertz or even 5 gigahertz. So it basically going to execute like billions of instructions per second, each second. And then CPU can run a couple of thousand instructions for one process, and then switch to the next process and then run a couple of thousand instructions. So that means CPU going to actually switch back and forth among these 8 processes, and in 1 second, the CPU going to switch back and forth like hundreds or 1,000 times. Now this is going to create some kind of illusion for each process, that each process is going to feel I'm treated well because CPU is actually treating me well, very well. Because this is going to cause the illusion that this system has 8 process CPU, and each CPU is serving one process. But the truth is there's only one CPU, because they use the time sharing technique. So you're going to create the illusion that you have 8 CPU, and that each of these 8 CPUs is called a virtual CPU. Okay, it's not a physical CPU. Okay, it's called a virtual CPU. Okay. Now, so the virtual CPU can be just an abstraction at the physical CPU, or it can be software that emulate the behavior of different CPUs. So basically, you can actually, give people some kind of illusion that you have a multiple CPU running on the computer system, but at the very bottom, there's only one CPU. Okay, that's the. Okay, let's talk about the benefits of virtual CPUs. First, a virtual CPU can provide a multi-user support. Okay, now suppose we have a computer with one CPU. Okay, now if the CPU is very powerful, then using the multi-programming environment, you can run a multiple processor on a single CPU, and each processor can be treated as, create some kind of illusion that each process is running on a dedicated CPU. Let's say process 1 running on this physical CPU. Process 2 is also running on a physical CPU, and process 3 is also running on physical CPU. But when the process is running on the physical CPU, it creates an effect, a kind of illusion that the process 1 is running on a virtual CPU. And process 2 is also running on virtual CPU, a virtual CPU. Now, so the virtual CPU use a fraction of the underneath physical CPU power. So let's assume the virtual CPU, the first one only use 1/3 of the CPU power. Okay, this one use 1/3 of CPU power, 1/3 of CPU power, and then the process 1 running on virtual CPU 1 can create some kind of illusion that the process 1 is running on its own CPU with only 1/3 of the power as the physical CPU. Same thing with process 2. And these process 1, 2, 3, they, each represented by one or more, they can actually share the same machine without being aware of each other. And in most cases, a virtual CPU can be run by multiple processors. Okay, let's say processor 1A, processor 1B, processor 1C. So you have multiple processors running on the same virtual CPU. Now this can actually create some kind of illusion that you have a multiple machine. Okay. Now sometimes you can even install a dedicated operating system called a virtual operating system. Okay. So that means the underneath computer system has one CPU and there's a one operating system. But then you can install a virtual CPU, a couple of virtual CPU on top of the CPU, the native. It's called a native CPU, and each actual virtual operating system can be used as just like an independent machine. Okay. Now the other benefit is actually like it's a multi-CPU transparency. So that means in the parallel computing, so people create a lot of applications, programs that they can run on parallel computer. That means a computer which contains a multiple CPUs. And then if an application can run, is basically written to utilize multiple CPUs, but also this application can run correctly on the multiple virtual CPUs. Okay, even if the underneath, there's one CPU underneath these multiple virtual CPU. Okay. Now the other one is a portability. So sometimes application compiled for one type of CPU, so it can run on a different CPU without being modified or even recompiled, because if the CPU is different, but you can build a virtual CPU which has the same characteristic as the type of CPU this application was compiled on. So these are the benefits of virtual CPUs. It gives people some kind of flexibility. You can run multiple applications on a single computer, and with only one CPU, and so you can also port, make the application portable from one CPU to the other, even though these are two different type of CPU. So these are the benefits of the virtual CPU. Okay. Another thing we're going to talk about is the modular structuring concept. Okay. Now, an application can generally be divided into multiple tasks. So if you create the app, it can divide into multiple tasks, each implemented as a process. Using multiple cooperating processes instead of one can have several important advantages. Okay, now I'm going to give you an example, but first let's actually talk about what are the advantages. So the first one is the interfaces between the processes are simple and easy to understand, because instead of actually creating a separate dedicated process, you can create a couple of processes that are related with a certain kind of connection. Okay, and each process can be designed and studied in isolation. So you can study each of the as independent processes, and the implementation reduces the idle time by overlapping the execution of multiple processes. We'll get to that, in an example. And different processes can utilize separate CPUs if available, and speeding up the execution of the application. Okay, so let's take a look at the example. Now, one of the example is the Microsoft Excel spreadsheet. Okay, so instead of creating one giant process running the spreadsheet, then Microsoft actually implement a multi, processing, and these processing are, somehow related. Now, for example, once you open the Excel spreadsheet, okay, so you can put some kind of information in the cell. You can even build some formula in the cell to, calculate the value of the cell based on the values of the other cells. So then you can create a couple of processes. You can create a couple of processes. Say, process one, you can perform a regular operation. So you can actually import the value into the cell, build a formula into the cell, and then in the meantime, if you actually want to if the Excel spreadsheet has a long list, now if you want to sort the information, say you want to search the student name, or you want to actually sort the student's name based on the last name, or based on the social security number, or based on the student's GPA, you want to do this. So basically you need to highlight some of the cells and perform some of the operation like sorting. So in that case, you can use another process 2, to perform, for example, sorting. Okay, and then you can use another process to do the calculation of the data in a cell and output the data into the other cell. You can use the formula in the Excel spreadsheet. Now each is running under different processes. Now, if this multiprocessing, in this multiprocessing implementation, now if there's only one CPU, okay, and then you can actually use the time sharing. So then the CPU gonna actually organize the time for process 1 and the process 2 and the process 3. They basically gonna switch back and forth among these processes. Now why this is not going to be able to improve the performance, because you are still running all these 3 processes on the same CPU. So you're not going to improve the performance. However, somehow you're going to make the program much better, because for some reason, if one of the process like a sorting takes a long time, so then using the time sharing, then the other process still going to actually, take the CPU time, because using time sharing, they're going to actually run same amount of time for process 1 and then same amount of time for process 2. The CPU going to switch back and forth among these processes. So if one process 1 is running a very short task, you're going to take a very a short time to finish it, then it's still going to finish earlier than process 2, which takes a longer time. Okay. Or if one process is blocked or stuck for some reason, then the other process still going to be able to run. Maybe the performance is going to be, slower, but it's still going to be able to run. Now, one of the benefits for the multiprocessing, building the app with multiple processes, is that if you actually running this Excel spreadsheet on the multi-CPU system, it's not like using time sharing. There are multiple CPUs, like 3 or 4 or 5 CPUs, and then you can run the Excel spreadsheet on multiple CPUs. So say you can run process 1 on one CPU, process 2 on another CPU, process 3 on another CPU. This is going to increase the performance. Okay. If that's the case, if there's a separate CPUs running the separate processes, this is going to, improve the performance dramatically. So that's the benefit of using multiple collaborating processes for an application. Okay, I think I'm pretty much done with section 1.2, 1.1, 1.2. So thank you.